Thank you, Laurent, and thanks everyone for coming today. And this bittersweet occasion is my honor to be involved. Okay, so I am a not a linguist. I have not studied formally the evolution of language. I'm a geneticist. And I've always been interested in the evolutionary genomic history of humans and our close relatives. And so I first met Kanzi in about 2008, I think it was, in Des Moines. And my former mentor and I and some others were visiting Des Moines to talk with Sue Savage Rumbaugh and others um, at the institute at that time to discuss possibly one time maybe looking at the genetics of Kanzi and other bonobos. I thought I'd begin today with an anecdote, though, because I figured this audience doesn't want to hear too many nitty-gritty details about genetics and genomics of bonobos. I'll tell a few things, but I'll start with a story. Maybe it was the third or fourth time I came to visit Kanzi, sometime in the early 2010s. And I have been watching YouTube and a lot of videos on YouTube. And I'd seen an evolutionary psychologist who was saying that, in his opinion, one of the aspects of humankind that separated that particular species from all others was our ability to appreciate music. And I thought that this was an interesting concept this gentleman had, but I was very suspicious that this was the case, actually, because I've seen many birds sing, and I understand that vocalization is very important for a lot of creatures. Anyway, I was in Des Moines. I was talking to Sue, and I asked her, Sue, what does Kanzi like music? Does he enjoy playing music or hearing music? Does he appreciate it at all? I was just wondering because of this YouTube video I saw. And she told me that, oh, well, Kanzi likes good music. He's very discerning, and he does not like when Sue, for example, sings or plays an instrument. But when Paul McCartney came to visit, he very much liked that music. And when Peter Gabriel came to visit, he very much liked that music. And all the while we're having this conversation, Sue and I, Kanzi's off to the side a few feet away from us. And if you know Kanzi and you visit him, you'll remember that he had a backpack, a day pack that he carried around with him often, in which he had various things that he needed or wanted at various times of the day. And at that moment, Kanzi took out of his backpack a harmonica, and he started to play it. And you know, making the music come from the harmonica. And Sue said to me at that time that she had not seen Kanzi take that harmonica out of his backpack for several years. And so to me, this anecdote shows that Kanzi was fully aware of what our conversation was about, and he wanted to get involved in that conversation. And I think that speaks to his understanding of language as produced by humans. And we were not as good at understanding his own language, but people are still working on that. There was a paper in Science earlier this month about language in bonobos and the production of vocalizations, and so that's an important thing that bonobos do. So I just wanted to briefly point out to the audience where bonobos fall in our evolutionary tree. And bonobos and chimpanzees, the other chimpanzees, our sister taxa that last shared a common ancestor between 3 and 1 million years ago. And about 6 to 7 million years ago, the three of us, humans, chimpanzees, and bonobos, all shared a common ancestor. Gorillas are our next closest relative, 7 to 8 million years ago. The four of us had a common ancestor, and orangutans, like Professor Matsuzawa mentioned, have a more distant relationship with us. The main difference that separates us in terms of our chromosomes is that human chromosome number 2, which is up here on the top left, is the fusion of two chromosomes that are seen in the other chimpanzees, bonobos, gorillas, and orangutans. And so those chromosomes fused together very recently in our evolution, and that's one of our distinguishing features genetically. Here's Kanzi'S karyotype, a picture that my colleague Henry took, Henry Hang, back in Michigan. Kanzi, like all chimpanzees that we've looked at, has 48 chromosomes compared to the 46 that we have. So we've looked at Kanzi's DNA. And one of the reasons we've looked at it, in addition to the language things, is because we're trying to understand what is it about the development of humans and other primates that makes us similar and makes us different. And one of the things we've noticed is that in humans, there are many problems in pregnancy, such as preeclampsia, that we don't see in other species, although we do see things like preterm labor in other species. It's a big problem around the world. It wasn't seen very often, preterm birth, in other species, but we showed that in this chimpanzee named Tulik, that she gave birth 3 times, all of which were premature labor resulting pregnancies. In one case, the baby lived. In the other cases, the baby did not. Chimpanzees have a much shorter gestation than we do. Bonobos are similar to other chimpanzees in the length of their pregnancies. So if we think about pregnancy in the terms of evolution, we can think in a sort of teleological way in which humans are at the top of the tree of life, as shown by this 19th century image. But now we know, because of methodological advances and so on, that actually humans are just one of the many vertebrates, all of whom share a common ancestor hundreds of millions of years ago. And now in a typical tree of life figure like shown here, we don't even see a human, we see a frog. And that is because frogs have evolved just as much as we have, and we are no more or less evolved than frogs or any other creature with whom we shared a common ancestor. One area that does evolve rapidly is our placentas. So human placentas shown on the left, which look very similar to bonobo placentas, look quite different than this antelope placenta on the right, for example. So one project we did was we sequenced the transcriptomes of placentas in all these different species of mammals that you see on your screen right now, and in order to look at the evolution of gene expression. And what we found is that this organ is the most dynamic amongst organs in mammals. And this figure depicts the 115 genes, and there's only 115 that are shared in their expression in the placenta across all those 14 species of mammals. That means that of the 20,000 or so genes that actually exist in our genome, a very small percentage is what are the sort of housekeeping genes that unify the placenta. And there's many changes on the human lineage, on the bonobo lineage, and so forth in the evolution of this organ. And so that's one way we can learn about differences of these species. Just to point out, I live in Tampa, Florida, and in this city, Tico means something very different than what it means to most of us today. Tico is the Tampa Electric Company. But the placenta that we sequenced in that last paper I mentioned was the placenta of Tico, a bonobo who lives in Des Moines, whose placenta we were fortunate enough to be able to get the genetic material from, with the help of Sue and Liz and everybody before the shift that came. The other main issue is that we study genetically is the increase in brain size in humans relative to other chimpanzees, bonobos, other apes. And we have a much larger brain. Other species have large brains like us, including dolphins. Elephants are relatively encephalized. By encephalized, I mean, what is the expected brain size given a creature's body weight? Our brains are about 6 times larger than you'd expect for a creature our size, whereas a bonobo's brain is also quite encephalized, about 2 to 3 times larger than you would expect. And so if we look at all the mammals that are alive today, what we see in the rainbow-like spectra here in primates is that there's a wide range of brain size in relation to body size. So the brain is very dynamic and evolving rapidly in our order, also in the order Cetartiodactyla, which includes the whales and dolphins. Within primates, what we see is that humans have this most encephalized brain, but chimpanzees and bonobos have relatively large brains for their body size as well. Actually, the second largest brain size for its body size are capuchin monkeys, New World primates from Central and South America. But one thing this tree shows that people often neglect is that brain size has often shrunk in primate evolution, including in colobus monkeys and howler monkeys, species that rely on leaves for their diet. And they have actually reduced the size of their brains relative to their body size. So the point here is that brain evolution is very dynamic, and it can change, and it probably will change again in the future. And that's all I'll say today about the work we've done. I'd like to thank you for your attention, and I'd also like to shout out my former mentor, Morris Goodman, who started our work with Kanzi, and who was the first scientist to realize that humans, chimpanzees, and gorillas shared a very recent ancestry compared to other species. He realized this in the 1960s, and he was very interested in knowing Kanzi and working with Sue. One of the reasons being he had a son who was had a lot of developmental delays, and he was interested in what about his son's brain was different than the brains of himself and others, and what was similar. And his main thing is that there's greater similarity across humans and apes than there is difference. And we learn a lot by looking at the similarities rather than focusing on the differences. Thank you.